So, by now, you probably know a few theoretical things about radioactivity, half-life. There are incredible numbers of resources in terms of your text, alternate text, PowerPoints, online video instruction that'll give you massive amounts of instructional theory on radioactivity. Some of it, of course, going way beyond what you actually need in Science 10. The purpose of this little video podcast is more to just focus in on some of the problem solving that you actually will have to do. So, yeah, we'll start with some of the simple ones, and then we'll just move on to some of the, well, potentially more complex ones. So, take a look at a problem like this one. What percentage of the original radioactive isotope remains after 4 half-lives? This one admittedly is rather simple because you're looking at starting off obviously with 100%, and of course half of 100% would be 1 half-life. 1 half-life you're down to 50%, 2 half-lives you're down to 25%, 3 half-lives you're down to half of that, which is 12.5%, and of course the 4 half-lives is going to bring you down to half of that again, or 6.25. So yeah, I don't believe you'll have any problem with a problem like that. So just to make sure here, realize that you're not actually expected to memorize half-lives. That the half-lives that you'll need for most of these problems will come from your data booklet. You'll be shown, the parent nuclei, say carbon-14, and then you'll be given the daughter nuclei and of course the half-life. So it's just a matter of you making sure you have that available whenever you're doing these problems. So a problem that actually doesn't use the table, but one where you're given the half-life is something like this one. The half-life of the radioisotope strontium-90 is 29 years. If you have 10 grams of strontium-90 today, 116 years from now, how much will you have left? This, of course, is a problem, like I said, where you are given the half-life already. It's not a bad idea to get in the habit of actually writing down the variables that you know, and so there's some conventional variables here that actually work, and probably the first one you might want to keep in mind is the actual symbol for the half-life would be just T and 1/2. So we're going to find a pen here. Where's a pen? That looks like a pen. And then we're going to go for like some ink. T 1/2. And in this particular case, problem says 29 years. So you write down 29 years. What we're after here, of course, is the total amount after 116 years of decay. So the total decay, I think I just said it, was 116 years. The other two variables are the mass that you have started with. Amount basically after decay is MT. So MO is equal to the original amount. Why don't I write that, just in case you need to use that in the future. MO is the original amount or mass, and in this particular case it's equal to 10 grams. And MT is what we're trying to solve here. So probably the second step in all of this is then to figure out how many half-lives this actually represents. So wherever you have 2 values for the same variable, in this case time, that's really what you're trying to compare. So 116 years is the total amount of time over the half-life, 29 years. If you divide that, you're going to find out that you actually have 4 half-lives. And of course, in reality, there are things like fractional half-lives, and you'll be pleased to know that in Science 10, we don't use them because the math involved gets a little messy, and what you will have to use is the decay curve to kind of come up with an estimate instead. So we're not there yet. We still need to find MT. We have 4 half-lives. Probably the best thing to do at this point then is to actually go to step 3, which is use a formula, and I'm going to show you that, but I think it's probably not a bad idea to probably clear what I got here. So we'll clear that off. And, well, you know what? We kind of need that problem. So we're going to put it back, and we're just going to try the lovely little eraser option, if I can find the beast. Hard eraser. There we go. Yeah, half an hour later, we'll be out of here. Let's go to brush size. As you can tell, I'm kind of learning this as I go, so you get to put up with the learning curve as well. Just about there, folks, just about there. So I mentioned that once you have the variables, the next step, of course, is to actually plug it into a formula. And in this particular case, the kind of formula you're probably looking at is mass total equal to the original mass, now divided by 2 to the power of the half-life. Okay, that's not a good idea either. Yeah. So back to this. So this is T1 half. And I believe we have just determined that MO was 10. And 2 to the power of, what was the half-life we just determined? We said that it was 4 half-lives. So if you actually carry that out here, you're going to have 10 divided by 16, which of course is equal to 0.625 grams. Lovely. Again, in a problem like this, realize that you probably could have done that without all of the naming of variables. You could have done it in your head. You probably could have done it using fractions. You could have done it percentage-wise. Whatever actually works for you is cool. It's not a bad idea to, for instance, look at a chart, for instance, from the alternative textbook for the half-life of strontium-90, to just kind of realize that if you are dealing with these half-lives, it's not a bad idea to get very comfortable with the idea that there's a progression from 100 to 50 to 25 to 12.5 to 6.25%. If you don't like percentages or dealing with percent, of course, you're dealing essentially with a fraction as well. So 2 half-lives is whatever amount of product you have to start with times a half times a half. If you have 3 half-lives, it's that original sample times a half times a half times a half. I think you get the point. Moving on. Let's try a problem like, not that one. What is the half-life of an isotope that reduces from 20 grams to 5 grams in 120 years? I'm going to stick to my lovely little 3-step process here just because I need that kind of thing. So in this particular case, write down the variables. That's not good. Let's go to this. Variables. T1 half. Did they give us the half-life? No. So we know that this is the variable we're actually trying to solve for. The other time variable, T, total, is equal to, and now in this problem they actually tell you the total is 120 years. We mentioned that we are comparing the original mass, which was 20 grams, with the final after decay mass, which was 5 grams. So again, this time we have 2 copies essentially comparing the 2 masses. So if you compare those 2 masses, just like we compared the 2 times in the first problem, you get a representation of how many half-lives. So in this particular case, you're asking yourself, how many times do I need to divide 20 by 2 in order to get 5? And the answer, of course, is 2. So 20 divided by 2 once is 10. 20 divided by, of course, 10 divided by 2 is 5. So that's the 2 half-lives. Step 3, if 2 half-lives equals 120 years, 1 half-life, which is what the problem is asking, is going to be 120. I mean, I'm going to write it down here just because you might like to see it. 120 years divided by the 2, I'm going to simply abbreviate half-lives as HL, 2 half-lives, and of course that is equal to 60 years. So we know what the answer is for this puppy. The answer is going to be 60
I would
years.
suggest that what you should do is actually try a problem like this one. Yeah, you could even just pause the video and then just check in a moment. Very similar, of course, to the last one. What is the half-life of an isotope that reduces from 80 grams to 5 grams in 120 years? Yeah. I will just work through it silently here, and then you check your answer here in a minute, and we'll just see whether you are in fact correct. So, in this particular case, oh right, I'm not supposed to be telling you. So, if you have just started up again, this little mess of scribbles basically was initially to throw down all the variables. We said, okay, we got the 120 years total. We're looking for our half-life. We started with 80 grams, and the decay process left us with 5 grams. So the real question you're asking yourself is, again, compare these two variables, see how many half-lives we've actually gone through. How many times do you need to divide 80 by 2 in order to get 5? And of course, I've just gone through the process. 80 divided by 2 equals 40, 40 divided by 2 is 20, so on and so forth. In other words, 4 times to get 5, so the half-life is going to be 4. So if it takes 120 years to go through 4 half-lives, 1 half-life is just going to be equal to 120 divided by 4, or 30 years. For the ones you've just looked at, there are probably an equal number of radioactivity half-life problems, especially with carbon-14 dating, that will simply give you a decay curve for the radioactive decay, very similar to this one of massive cesium-124. So a typical problem here that you will have to answer would be something like this one. Using the decay series for the mass of cesium-124 versus time, which of the following times is the half-life of cesium-124? So obviously you're looking for half-life. You're, in this case, given the fact that you have, oh my goodness, we're going to get this right yet, folks. We have in this problem to start with 20 grams. We're just looking for how long it takes to go to 10 grams, right? So 10 grams would be one half-life. Follow the 10 grams over to, look at that nice straight line. You, of course, would use a ruler, take it to the decay curve, and then just basically follow it down to, I would estimate that it would be right in about here. At least, given the options you have, you've got 10 seconds, 30 seconds, 50, and 100. It's pretty obvious that in this particular case, we're looking for basically a half-life of 30 seconds. Right. How about this one? What mass of cesium-124 is left after 2 half-lives have passed? So we're looking at mass. How long did we say 1 half-life was? We said that 1 half-life was going to be 30 seconds, so 2 half-lives is going to be 60 seconds. So you go over to 60 seconds, follow it up. My goodness, here we go again. 60 seconds to the decay curve, and then over to the mass, and you can tell that the mass of cesium left after 2 half-lives is 5 milligrams. Right. Interestingly enough, one of the questions that I think it was number 29 on the study guide asks you to solve for something that you actually mathematically in this course can't do. And the reason you mathematically can't do it is because they're presuming you're actually going to be using a decay series. You can, of course, take calculus and math 12 in order to calculate where that is on the line. But in this particular case, they actually expect you to use the decay curve for carbon-14, which, by the way, is readily available. This one comes, I guess, from page 303 of your textbook. See, if you have the decay curve for carbon-14, it's not really that bad to say, okay, hair sample at 80% on the decay curve, hang on a sec, is going to be right up around, let me see here, yeah, 80% right there, and then we'll just follow it down to the bottom, and I'm not going to try to draw it because it'll be really ugly, but it's just slightly less than 5, so I would say it's around 4, and because that's in thousands of years, you would say that it was for 4,000 years. By the way, if you're still working on that study guide, the problem that follows that one, number 30, uses that same carbon-14 series as well. So the more of these problems you can look at, probably the more comfortable you're going to get with half-life. We still have a little section on fission and fusion to do from chapter 11, but you might find it valuable at this point to even start the random test because there's an awful lot of half-life questions on there that would give you great practice. Thank you for watching.